So we will resume our discussion with regularization, talk about overfitting and then bias and variance, and then move on to our next topic, which is classification. Okay, so recall that the reason we talked about regularization is because of our observation that we are able to fit points to arbitrary levels of accuracy by increasing the degree of the polynomial. This contrasts this linear fit with a higher order polynomial. And we are in general concerned that a new query point or a test point might not necessarily follow this very complex pattern, because the complex pattern is not just an artifact of the data of the actual model underlying the data, but is also an artifact of the noise. Okay, and your new query point might be here. So would you use the line or the curve? That's the question. And we said let's put some penalty, associate some penalty with the W's, and we tried and illustrated this with regression plots. So you see that here, as you increase the power, you get arbitrarily complex polynomials for sure, but what we also observe is if you kind of look at the W's become very large. So we said let's try and do regularization, and we also provided a Bayesian view of regularization using a prior, and the prior basically corresponded to each Wi being a normally distributed random variable with mean 0 and variance 1 upon lambda. So with that form, the W map corresponded to this L2 regularized square loss, and let's look at what effect it has. These are the L2 regularized components, and what we observe is if you try and plot the number of lambdas which are zeros, okay, W's which are zeros for different values of lambdas, okay, and you find that there are hardly any zeros. So the W's become small in magnitude, but they are still irritatingly not zero. And this is with L2 regularized loss. Then question is, what happens if instead of L2 regularization I used L1 regularization? Can we contrast their level curves? So indeed we can. So on the left hand side is how the level curves of L2 look like. They are basically concentric circles. So almost every value is equally possible along the periphery of the circle. On the other hand, if you look at the level curves associated with L1, they will turn out to be of this form. They are basically squares, but with their corners on the coordinate axis. Okay, this is L1, the one norm is constant, and what we observe are these corners. And this means a lot to us because there is a tendency now for parameters to have some zero components. I gave you this analogy that if physically also we find that when there are corners, edges, the dust tends to accumulate there, and that we find with points as well. The points tend to accumulate at the corners. Okay. And this is Lasso regularization. To convince yourself in other ways, you can also look at the map or the Bayesian interpretation for Lasso, and that turns out to be coming from this Laplace distribution. The prior for W is a Laplace, and what does it look like? Well, let's contrast this with the Gaussian. So Laplace says it's proportional to Wi minus mu divided by B. If you had a Gaussian prior, basically you had exp of Wi minus mu. Well, mu was 0, that's what we chose, but in general it could be something like this. There's a negative sign, exp of minus of x, something. We know what Gaussian looks like. Any guesses what Laplace looks like? What would it look like plot wise? Okay, this is how it looked like. So as I said it, it will not be differentiable at 0. Okay, so here's the plot. The Laplace prior yields more sparsity even as per the Bayesian interpretation. So that's why Lasso is sparse. Okay, so the sparse solutions. I mean basically the probability peaks at this point. So the tendency for some W's to go to 0, or rather W's will become non-zero only if required. Why do they become non-zero at all? Not all of them will become exactly 0, right? Because you will need to also explain your data. So data will come from the first component. So they will become close enough to 0. They will become close enough to 0 but not exactly 0, or in other words they will become non-zero to the extent required to explain the data, because there is a non-zero density at other places also. Result peaks at 0. Okay, we called the Gaussian the Hare because it yields itself to a closed form solution. Ridge regression estimate, that is phi transpose phi plus lambda I inverse phi transpose y. okay, but Laplacian is a tortoise because there is no closed form solution. So can be only solved iteratively. And I had explained the algorithm, the lab session, but here is a quick look. What you do in Lasso, first of all you realize that Lasso has this least squares objective. This is a least squares objective, and in addition the one norm on W. So you keep iterating till the, let's say, the relative loss, relative drop in the error across two iterations k and k plus 1 is not significant, right? Keep doing this until that happens. You could, you could also look at other criteria, but this is one. And what you do, you find the least square iterate, which is take the Lasso iterate from the previous iteration and do a gradient descent with respect to the least square, right? And thereafter you adopt something called the proximal step. What proximal means, I have provided you some reference to my notes on optimization, but then what proximal basically means is you try to find the closest approximation to the least square iterate which has the smallest L1 norm, or smallest L1 norm in comparison to the proximity to the least square iterate. Okay, so that's why it's called proximal. But let's look at what the algorithm gives you. It says that the k plus 1 Lasso iterate at coordinate I, this is ith component of the W. So that is obtained as 0. So let's look at this case. It is 0 if the following holds. So if your Wi is between, say, minus lambda eta and lambda eta, then it will be 0. This is the segment that we are referring to here, it's 0. Okay. So moment it is small, you kind of push it to 0, small relative to lambda eta and minus lambda eta. Otherwise you are going to shrink it, right? Shrink it in the sense in magnitude. So both these steps shrink Wi in magnitude, in absolute value of Wi. So if it's greater than lambda eta, reduce it. If it is less than minus lambda eta, increase it in the sense of making it go closer to 0 because it's already negative, but reduce it in magnitude. Okay. So this again, should I explain, the algorithm basically says we achieve exactly what we set out to, get you more sparse solutions. Is clear? Okay, so we have seen this in 3 different ways: level curves, the Bayesian estimation, and the algorithm also. Okay, so note how Lasso yields greater sparsity, and again I recap from these are level curves I was talking about. The sparse models are self-evident, and as you can see here, for large values of even reasonably large values of lambda or relatively large values of lambda, many of the W's go to 0 to the extent of making the model look silly. It's like lambda is 0.01 and you're you'll see that even with high degree you get lots of 0 W's, making it linear all the time, right? And let's just plot the number of 0 lambdas, number of w's that are 0 for different values of lambda. Okay. So as you can see, very quickly several w's turn out to be zeros. As lambda increases. Okay. Exactly the level curves. The level curves are the best intuition. These have no corners. L1 has no corners. That's why I keep giving the example of dust accumulating in corners. You find that physically also, right? That's intuition. Any other question? So what we are going to do is study this trade-off between fitting the model on a data set and preparing it for generalization, right? You can basically mug up for your midsems and endsems, but then how do you make sure that you do well in the real world? So then how do you design your exams? That's a question. So how do you design your data set? Think of exams as your data set, right? So we don't want students to overfit in their understanding of machine learning or any other topic that we teach. So how do you generalize well enough? That's the question we are trying to address. Okay, so it's also, think of it as design of the data set, and I'm going to try and justify this data set design, this trade-off between generalization and overfitting through bias and variance. Okay, so we understand what is bias and variance very quickly. So let's we have seen how to estimate linear predictors by minimizing a squared loss objective. How do you know that your estimated predictor is good? One thing is training error, right? But we already seen in your assignment, lab assignment 1, part 1, tutorial 2, where we saw that the ridge regression estimate will always have lower error, higher error than the least square solution. Okay, so training error is not good enough. Else the least square error obtained using the ridge regression will always be greater than the least square error using the least square estimate. I mean, this makes the ridge estimate look silly. So his question is it unfair? Isn't it unfair to do this computation? That's exactly what I am claiming. It's unfair. But then most of the times what you have been evaluating is the sum of square error. That's all I am saying. So I am pointing out an obvious finding that some of you have. His point of unfairness is that you computed the ridge estimate using some ridge objective, and why are you computing it on least squares? Well, by the way, I mean, this doesn't make sense to compute ridge objective as an error function, because ridge had something else in mind, which is also generalization. Why should I put why should I put either an L2 norm or an L1 norm in my error? This doesn't make sense. So he is right about saying that it is unfair, but that doesn't mean that you will be it will make sense to plug in the regularization term. Is that clear? The second is test error. So training, all this is fine, change the data set. So measure your sum of squares error, but not on the data set on which you computed the least square estimate. Sorry, question. Greater than equal to, yeah. Actually, since there is strict convexity, it will be greater than, but if you, that is assuming lambda is non-zero, doesn't hurt to put an equal to here, but it's actually strictly greater than if lambda is non-zero. Test error. So what is test error? It's saying that, well, I will not compute E, but I'll compute E tilde. I'll compute E tilde ls on W, which is nothing but summation over I in test data of yi minus W transpose phi xi. This I, this test data is not what was used to obtain your W, right. So W, assume that W minimized some, I mean it could be just the least square objective, but it did so on the training data. Okay, so this basically says don't test, don't generalize the performance of students just based on what they have learned in the class, right? And this typically is the crib about most of the quizzes that are conducted in IIT, that the mid-sem and end-sem questions don't look like the tutorial questions, right? I mean that's just basically because we want to ensure that the learning generalizes. So that rote learning doesn't work. So the test error is to avoid rote learning. So test prepares against rote learning. Is clear? No, you'll be using the training data to estimate the parameters, right? What will you do with the training data, guys? If W also comes from the test data, your test data becomes the training data. The W has to come from some data set. So I mean, it's like asking why don't we use the end-sem for tutorials, right? Then so you have a new overfitting problem. Okay, so in general, what do you think the plot of prediction error versus model complexity will look like? I want you to think. So think openly. I mean, you apply whatever intuition you want about the x-axis. Model complexity could be number of the degree, for example. Say, let's say the degree of the polynomial. That could be the model complexity. Prediction error that we already seen. Okay, now tell me what do you think the plot will look like? So as the complexity increases, now prediction error, sum of squares error, I didn't specify on what? Train data or test data? Test data. Okay, so let's start with training data. So on training, what do you expect? very quickly decreases, right? On test, what is the behavior you expect? So in test it will not just be that it will be exactly opposite of training, that doesn't make sense. I mean the training after all is some cousin brother of test, right? So it's just that it will not mimic it exactly all the way through. To some extent it will, and then it will diverge. So how do you think the plot will look like? It will initially, yeah, so I'm not going to draw them on the same scale, though often the error will be slightly higher on the test even in the beginning. It might increase again and decrease again, but then yeah, this is roughly the tendency you expect. So we are dealing with multiple things here. We are dealing with the complexity of the model, we are dealing with the distribution from where the data came, right? We are dealing with how much the model differs from reality, how complex it is and trying to mimic the reality, and what is the data that is trying to fit in the first place. Okay, so it's best to deal with these variations in the model as well as in the data set through probability. So basically through expected value, right? We are looking at expected behavior. This is the expected behavior we are trying to model. Okay, so in an expected sense, so please expect a lot of expectation to come up in some of the following slides. Why? Because we are talking about distributions. So we have, moment we talk about test data versus training data, we are concerned with the distributions because it's a spectrum. Is it making sense? The distributions that underlie both the generation of the y's. So what are the distributions we talk about? Right, we have talked about y, right, and we said y, it's some normal blah blah blah. That was one way we looked at distribution. Okay, we could also have x coming from some distribution. X itself could be from a distribution. Let me use distribution for both. Okay, so there is some distribution on y, there is a distribution on x, and the generation of x influences the generation of the y's. The model on y also is also factors in the error component. There is an error also, right? Okay, so this is plus the measurement error which we have talked about so far. Okay, so put all of them together, the three main sources of test error. We will now show that the components analytically are bias, variance and noise. So this epsilon we talked about, we mentioned, we said it is noise, right? So we already to some extent looked at noise, but now we look at noise in conjunction with two other components, bias and variance. Okay. So let's get an intuitive understanding what we mean by all of these. So let's again look at a polynomial plot, and interestingly all this becomes very easy to demonstrate for regression. We are taking regression as a running example for many concepts. Okay. So far we took regression as a running example for Bayesian estimation, and all that will also help more complex problems, I mean different problems which could be a regression plus classification, for example. Now we will see again observe a phenomenon which will also recur in other settings, but just becomes easy to visualize. You see this polynomial fit, so not you see a polynomial fit and also the a linear fit. Actually let me correct myself. So the data is come from a true distribution, true function. So we will keep referring to the true function as g. This is a true function which looks complex. I may try and do a polynomial fit on this, I may not get this far, right? And let us say this is my linear fit. I will refer to this as f. So f is my fitted hypothesis, g is my true function for the rest of the discussion. This is clear? And from this true function there are some sampled points. But are they just sampled, or is there something more that is added? Do you see some noise? Right, with additive noise. So there is an additional noise component here, and that is what makes these points not lie exactly on G. Okay, so the three components here, the fitted hypothesis, the true function, and some deviation of the samples from the true function through the noise. Could be measurement noise, right? It could be recording noise, corruptions that could occur. Measurement noise could also be because of device imprecision. We will not get into that again. We gave the case of epsilon already. Now let us say I sample multiple times, so I keep sampling, right? So the points that you saw, the sample points, I keep sampling. Every time there is a small noise component, and every time I do I fit the f. Okay, so the f's have been fitted. What has happened here? Points, a point set of points has been sampled multiple times, and for each set of sample points f is fit. Now you will see that there will be some variation because the sample changes, the epsilon error will be there, and then this is expected, yes or no? Now how much is the spread across these guys? Is there too much spread in the case of linear fit? Are they changing drastically? Yes or no? The fits are not changing drastically, and that is the observation. So the deviation of these fits with respect to the mean fit is not much. okay, and that is because we are dealing with a linear fit. For some other fit, imagine if I were to do polynomial fit, as the points keep changing, would the curve dance more than the linear fit? It will change more because if, it's more sensitive. This is not as sensitive, right? So this is what we model through the variance. The variance that you get by perturbing your estimates, perturbing the points and getting the estimates subsequently. So I'll try and show variance in blue and bias in red. Okay, just remember this color coding. Okay, so this deviation of fits as sample set changes, right? The data sample changes. Now the second part, bias. Now what happens to bias? Do you see that the true fit and the true function and the fit, they are actually quite apart from each other? Why is that so? So original function is non-linear, you forced a linear fit. Okay, so this is bias. The difference, I mean, I'm using difference very loosely here, difference between true and fitted functions. Again, we are going to view this through the lens of the sample data set. Is clear? So let's write that down on board, and this is all very intuitive. So deviation of fitted f from the true G. See, variance is only a function of f. Do you see that? Variance just says how much f changes. Deviation of fits f1, f2, etc. as sampled set changes. So it's only deviation of f from its own mean. Whereas red, the bias, is the deviation of fitted f from the true mean. I hope this point is clear. Okay. But now we will show this mathematically. And before we get to the math, let's look at the last component, the noise. Right? We already said that there is this epsilon noise. For example, right? For example, we had this epsilon noise which was n0 sigma square, and we said y equals, so basically y was obtained using some underlying function g x plus epsilon. Okay. Now, for example, as I said, for example, so that's the third component, noise. So deviation of sample from true G. So all this, whatever I'm writing on the board is plain intuition. And what is overfitting? Let's get an intuitive understanding of pretty much everything we have discussed so far, right? Overfitting. Overfitting is when the proposed hypothesis fits the training data too well. Training data is again what? You have to understand it is coming from an underlying G plus noise. So now hereafter you should develop that view. And sorry, noise need not be always additive, it could be multiplicative. Okay, we will make some assumptions about noise. Yeah. So we, we were trying to look at variance independent of noise. Variance, we were looking at just a deviation of various fits with respect, with respect to the mean of those fits. What is underfitting? See, all of us expected that the test error should initially decrease as complexity increases, right? Yeah, it's not that complexity is always bad, but if your model is too simple, then you have underfitting. When the hypothesis is insufficient to fit the training data, by design you are too far away from the training data. So I hope this contrast is clear. Overfitting and underfitting. Overfitting is you take the data, training data so seriously that you kind of don't do well on test data. Underfitting is you don't do well even on the training data. I mean, you may if you philosophize, right? वैसे भी real life problems look very different from our midsems and midsems. Why prepare for exams? So that is underfitting. I mean, so obviously we don't want underfit models. Okay, so now how do you kind of look at how these interact? I mean, so far we have not studied their interaction. Now we look at, we'll mathematically derive their interaction. Okay, and that's through a decomposition. Okay, so let's say the underlying distribution is y is gx plus epsilon, where epsilon is the true function, and this is an assumption. Okay, now we are going to do this interaction under assumptions. So I am not claiming to do this interaction in general. We understood their those individual concepts in general, but now their interactions will derive under certain assumptions. This assumption, the epsilon has mean 0 variance sigma square. I haven't really assumed that epsilon has a Gaussian distribution. That I haven't assumed. It just means 0 variance sigma square. So given a data set of m samples, we fit a linear hypothesis. For example, this is an example. Where FD is W transpose X. So FD is F fitted using D. Here we will drop the subscript D starting the next slide. So for us, F, the fitted function, is actually fitted on the data set D. So FD and F mean the same for us. So for example, you may minimize the sum of square errors. Okay. So the linear is not going to be assumed hereafter, that is an example, but let me just highlight what we will be assuming. So we will be assuming that we are minimizing the sum of square errors, that much we will assume. So we assume that epsilon is random variable with mean 0 variance sigma square, the noise is additive, and we are minimizing sum of squared errors. Okay, and let us say we have a new test point. Okay, so the new test point will be y hat equals g of some x hat plus the epsilon error, and I am going to compare that with f of x hat. So the new test point has come from the true function plus some additive noise, and I am going to compare that against the fitted x, fitted value as per f, the model f. F for example could be linear, but it's not necessarily linear, we are not assuming it hereafter.
So, have you highlighted that we're using mean square? So, as far as I think, it should depend on what kind of variable.
Yeah, so broadly speaking the decomposition we'll talk about will hold in many other settings, just that it's easier to show the decomposition. The form, there will be some slight changes, okay, if you don't assume sum of squared, but then the spirit is going to be the same. I have already kind of illustrated that graphically, the spirit is, but then the interaction we need to get into the details of the error, for example, that we are pivoted on. Okay, so we are assuming that y hat is obtained using this. So now for us the query is this basically, what is the expected test error? As I said, we'll use the lens of expectation because things are changing, the data set, the noise, sorry, sample, the noise, all that is subject to some distribution. So therefore we look at the expected value of the fit f x hat is a query point, minus y hat which itself has this form, the whole square. It's expected value of the square. Okay, this is what we will decompose, and largely speaking this is what will look like. This will be bias square plus variance plus noise. This is what it will look like. Okay. So I don't want to leave any suspense. The decomposition is basically this. Now what is this bias? We will see what is this variance. Okay. And I tried to kind of stick to color coding. Okay, so I want you to do the following. I want you to prove the following from your basic course on statistics. I am sure you have done this from CS337, right? So the expected value of x minus expected value of x square. To this, if you add the expected value of x, the whole square, then you will get expected value of x square. This is the central thing that will keep recurring. So please write down this starting expression. I'll give you a few minutes just to understand how this decomposition has been used. Okay, so what we have done is, I'll explain just the steps. E of f x hat minus y hat, that's what we set out to, the square, expected value of this. In the first step, I have just expanded the squares, right, expanded. So I have E of x inside the expectation f x hat square plus y hat square minus 2 f x hat y hat. This clear? Then what have I done? Then this part, so I have, now you know that expectation of sum is sum of expectations. So I want everyone to write and just explain the steps. The second step is also straightforward, then thereafter I want you to think. Third step is where you have to apply this. So G is the underlying function, right? That gave yeah. So Gx is what gave you y, modulo and epsilon error. So G is the true function, F is a fitted function. So that's a good question. The first step you should have had expected value of fx hat into y hat. How did we write it? As a product of two expectations. So when you apply expectation to this, how do you get a product of two expectations? What have we done? We have basically assumed that process of sampling the data is independent of the, so y hat is obtained from epsilon, right? Fd or f is obtained by a sample. So the sample and the noise are not directly, the noise injection process, which is additive, are independent. So that's a good point, we have assumed that. This epsilon is added to gx hat to get y hat, right? Whereas the data set also consists of the x hat, however the points are being sampled first and then the noise is being added. So for this error point, see this is y hat, right? So the y hat has an error which is that is independent of the error that was used to generate the data set. So this y hat is one specific query point. It has its own epsilon or epsilon hat, if you want to call that. Is that clear? So there is some training data I had generated from where I fit this function fd, and now for a new query point I have an epsilon. Yeah, but it depends on the data that was used to fit the function, right? So data was sampled. So expectation, the expectation is over the sample, data set sampling, and so what are the distributions, right? One is the data set sampling and the other is the distribution associated with the epsilon. Okay. And here we are assuming that train sampling D and test error epsilon are independent. So is that clear? So that answers your question, why the expectations multiply. You know that expectation of product of independent random variables is product of expectations. E of xy is E of x into E of y if x and y are independent. So until this step should be clear, because in the third step all we are doing is making use of this fact which I have also written on the board. We are simply expanding E of fx hat square as E of fx hat minus f bar x hat. F bar x hat is nothing but, okay, so I'll write the same thing there. For us this is like fx hat, this is E of f x hat with respect to the data set, which is the same as f bar x hat, the second component. This component Ex is again the same thing here, E of fx hat, which is f bar x hat, and this x, well, x for us is, so following that step I am now leaving some work for the next slide which is marked in red. All I am saying is E y hat square which followed, so E y hat remains here, E of y hat square, E of y hat square, this whole thing just remains around till the last step. In the next slide what I am going to do is I am going to apply the same identity to E of y hat square. Is that clear? So this when I say same identity, I am referring to this identity. This identity. So try doing that. What will happen? If you now apply the same identity once more to E of y hat square. Okay, so far I have shown you how to apply the identity. Now you assume that this x square is now y hat square. Apply again, everything on the right hand side will be in terms of y hat square, where you have to remember that y hat is g of x hat plus epsilon. I sampled a training set, fitted a function f, and my new observation query point based on an x hat, I had an epsilon noise corruption while observing my y hat. So you can write in words every step that's going on here. I won't have the time to do that, but I hope you can follow suit what I tried explaining just now. Right? So we want to expand the sum of this the expected value of the square of the observed corrupted y, where the corruption is with respect to the noise, based on g, the true underlying function. Can you do that? Just apply this, the same identity to E of y hat square. Let me know what you get. Oh no, G, it says G. G, B bar you won't get. No. So again, good question. So the question is E of y hat and G of x hat, right? That's via that. Okay, so good, very good question. So what is y hat? Y hat is G of x hat plus epsilon, which has mean 0 and variance sigma square. Okay, so E of y hat is E of G of x hat plus epsilon, but G of x hat is not, x hat is already given to you, sampled from some distribution, but x hat is given to you, G is a true function, right? So this will be E of G of x hat will be just G of x hat, and E of epsilon is, what is the expected value of epsilon? 0. It's G of x hat. Good. So keep asking questions. I mean, demand explanation for every step here. But expected value of G of x hat, expectation, G, see, G is a deterministic function and x hat is a query given to you already. It's y hat that has come from a distribution influenced by epsilon. See, there are two distributions we are talking about. The distribution from which the data was sampled, right? That was already history. And for the query point, I have some corruption epsilon. That's what I have written there. Expectation over data set sampling, and which had its own corruption epsilon, etc. And the distribution of epsilon, if you want to be more specific here, distribution of query epsilon, epsilon for query. Okay. So what happens if you do the substitution? Substitute for the E hat y hat square. Okay, you get this. Yeah, obviously, yes. But what do you get? So here, so we just applied the same trick, the trick there on the whiteboard to have E of y hat square. So this E of y hat square, when I expand, I get exactly this form, because y hat is g x hat plus epsilon. So, and I am going to now substitute here g x hat plus epsilon, I mean, or you can just keep it y hat, and then I'll basically need to what is the Ex there we are talking about? The Ex is just G of x hat, the same thing which I explained in the previous slide. So E of y hat is just G of x hat, or again if you want to go back, is E of G of x hat minus or plus epsilon, which is G of x hat, plus expected value of epsilon, which is 0. Okay. So these are the three components you can get. Now this, the part in blue is exactly the variance. The blue part says, I mean it has this f bar x hat component, but if you compact it, what is it? It is how much are the estimated curves changing with respect to the average curve. So just read out the text. Deviation of fits f1, f2, etc. as sampled set changes. The part in red is telling you how much the y, when we combine that, we get how much the y, how much the f is different from g. Okay, I am just going to expand that next. Okay. So we have these three components. When you now you need to just do a little bit more work to just kind of clean up those expressions. You will get exactly this expression, which is expected value of f of x hat minus f bar x hat square. This is what is called the variance. How much the f's vary with respect to their average. How far is the f from g in the average sense. Okay. How far is average of f away from g? That is a bias. The variance is variance of f with respect to its, of course, the average fit. And the third we already know, y hat minus g x hat is epsilon. So the third part is nothing but expected value of epsilon square, which is sigma square. The noise, this is a noise or the variance of the noise. Okay, so the second part is the bias. You can call it the bias squared if you want. Variance plus bias square plus sigma square. Exactly what we set out to prove. Okay, so just again, bias is G, the average error of G. Variance is, oh I am sorry, there's a small flip in notation here. This should be F, this should be G. I forgot to, so I just changed the notation. Bias is average F, how it varies with respect to G. Variance is variance of F, and noise is the deviation of the square of the deviation of y from the true function, the underlying function G. It is a squared, therefore sigma square. This is a noise that you cannot reduce, called irreducible noise. So the same thing I have just tried to present in another slide. Now just to sum it up, so what happens is, there is a nice figure. So there is always this trade off between bias and variance. So let us just keep this aside, this exact derivation for under certain assumptions, but what you want is low bias, low variance. Here is the target, right? Imagine you are shooting. How many here are good at shooting arrows or bullets? Anyone? Okay. So what is, so you have low bias and low variance. We'll verify that in the lab session. Probably, maybe this will be the next lab session. You just get to shoot. So that's what we want. This is desirable. This is what is desired. Everyone agrees this is desired. Each of the dots is a different shot. Every time I shoot, I hit the bull, I hit the red center, right? On the other hand, high variance, low bias, it says, oh well, on an average I am hitting the red, but I am moving too much around it, right? On an average, I hit red spot, but move too much around it. And here's the case of high bias, low variance. I am consistently missing the target, but I am very consistent. 2 centimeters away from target every time, and exactly 2 centimeters in the same direction. So that's very consistent, but bias, right? So this consistently or missing the target in a consistent manner. It's not just about consistent. And high bias, high variance is आंखों पे पट्टा shoot कर रहा हूँ, right? So that's the case of high bias, high variance. I hope this is clear, and that's the exactly the trade-off. So model selection is given the bias variance trade-off. How do we choose the best predictor? And that's why we design data set, train and test data set. Repeatedly sample observations from a data set with replacement. You take one sample, for each bootstrap sample, leave out some sample. That's what you do. So you keep your dB, from that you subset VB, left out, right? So you have dB minus VB. So you fit your model on dB minus VB and evaluate it on VB. This is the real sutra. Take out a sample VB, train it on dB minus VB, and you keep doing this for every VB is just an index, okay? And then you compute the bias and variance. This is how you would measure bias and variance, say using the bootstrap sampling. You compute the bias and variance with respect to the fits that you get on the dB which has VB removed. And this is the spirit of train, validation, test split. You divide the available samples into three sets: the train set, a validation set, and test set. Okay, and we'll develop more on this in the lab session, but the idea is train is used to train the algorithm, learn the parameters. Validation is used for model selection. Okay, so if you use train to learn W, you use the validation to tune the lambdas, and you'll use test to report error on X hat. That's the story. Okay, and this is how you hope to kind of do the best you can with respect to your chosen model on bias variance.